Hello, my name is Amy Zimmerman. I'm pleased to share some of our ongoing work evaluating search algorithms and search parameters for 15N tracking proteomics. Mass spectrometry-based analysis of entire community proteomes has become a powerful tool in recent years for investigating the complex functional interplay within microbial systems and microbiomes. The use of stable isotopes in combination with proteomics analysis provides an elegant approach for tracking nutrient flows into newly synthesized proteins and linking specific taxa with active metabolic processes. But few bioinformatics solutions are available for capturing differential protein labeling within and between organisms in mixed communities. Here we extend our previous development of a pipeline for quantification of peptide-level isotope enrichment from metaproteomic data. By evaluating the impact of the number of variable modifications considered during peptide spectrum matching on peptide identification rates and enrichment estimates, that work was done using the sequest algorithm with percolator for post-processing, implemented in Proteome Discover, which is the peptide spectrum matching workflow our pipeline was originally developed with. And we also adapted our pipeline, which we call CPI, for use with open source search algorithms as an alternative to Proteome Discover. Specifically, we tested MSGF Plus and MS-Fragger. As I mentioned, we named our pipeline the CPI pipeline for classified peptide isotope enrichment. Briefly, peptide spectrum matching is performed against a site-specific database with variable modifications to accommodate 15N substitution at any atomic N position. For each peptide identified, the mass to charge values representing all possible isotopologues, that is from the completely unlabeled peptide to the fully 15N labeled peptide, are generated using the monoisotopic mass and combined with retention time to extract MS1 intensities and estimate isotopologue relative abundances. Relative abundances are then corrected for natural abundance isotopes using the R package isocorrector, and peptide mean isotopic enrichment is calculated as atom percent 15N. In the last step, to ensure reliable estimates of 15N enrichment values, we developed a classification model based on training data from cultured biomass of known isotopic enrichment. To evaluate search algorithms and parameters for this analytical pipeline, we generated data from bacterial cultures grown for multiple generations on known atom percent 15N labeled media. The Cyanobacterium synechococcus was grown in media with 15N nitrate at natural abundance 1, 2, 5, 10, 20, 50, and 100 atom percent 15N. This data was used to calibrate the CPI classifier. The phototrophic purple bacterium Rhodobacter capsulatus was grown in media with 15N ammonium at natural abundance 5, 10, 25, 50, 75, 90, 95, and 100 atom percent 15N. Peptide samples were separated on a capillary C18 column for 3 hours, and spectra were generated on an Orbitrap Elite in data-dependent acquisition mode. Peptides were identified using sequest with percolator in Proteome Discover, MSGF Plus with percolator implemented in OpenMS, or MS-Fragger with Philosopher in the command line. Atom percent 15N in each identified peptide was then determined using the CPI pipeline. Perhaps unsurprisingly, we found that peptide identifications declined with increasing isotopic label. But we were able to show that this trend occurred across a range of variable modifications considered during the peptide searching. For this, peptides were identified in spectra from the Rhodobacter capsulatus data. The points are colored by the maximum number of variable 15N substitutions considered per peptide, from 0 to 20, 20 being the maximum permitted by sequest, as well as fixed 15N labeling. The shapes represent the peptide spectrum matching results before or after the CPI classifier was applied, showing the mostly slight reduction in peptide identifications after classifier filtering. One thing to note is that some degree of 15N variable modifications must be included during peptide searching to identify, let alone quantify enrichment of peptides with greater than about 10 atom percent label incorporation, as shown by the steep drop in the yellow line here, which considered 0 variable 15N modifications per peptide. Samples in the range of 75 to 90 or 95 atom percent 15N are the most challenging to detect and quantify. Fixed 15N modifications are required to detect an appreciable number of peptides in highly labeled samples, and those are largely filtered out by our classifier. So this is a clear area of improvement. We found little variation in peptide identification rates between 5, 10, and 20 variable modifications across a range of enrichment values. indicating that the number of variable modifications allowed had a limited impact on the peptide spectrum matching. But it does have a large impact on the compute time. For samples with 10 atom percent 15N enrichment, a search considering 0 variable modifications took less than 1 hour, but rapidly increased to several hours per sample for 5 variable modifications and to over 30 hours per sample for 20 variable modifications. We also found that peptide identification rates declined with increasing isotopic label across search algorithms. For this evaluation, Synechococcus data was searched with Sequest, considering 20 variable modifications, as well as with MSGF+, allowing 3 variable modifications per peptide, or MSFragger also allowing 3 variable modifications per peptide. Taking into consideration that the maximum number of variable 15N modifications allowed during peptide spectrum matching varied among the search algorithms tested, we found that peptide identification rates declined more quickly with alternative search algorithms than with Sequest. That said, we found that in samples enriched 20 atom percent and below, MSGF+ identified a comparable number of peptides to Sequest with a much faster runtime, on the order of a couple of hours per sample rather than tens of hours per sample. While this analysis compared the number of peptides identified by different search algorithms from a range of isotopically labeled samples, we also wanted to understand how the accuracy of peptide enrichment estimates compared across search algorithms. This plot shows the estimated peptide 15N enrichment values on a log scale for Synechococcus cultured on different atom percent 15N media using parameters from our original development of the CPI pipeline, that is, Sequest with 20 variable modifications. Here, the median is shown with the 25th and 75th percentiles. Although there is some spread in estimates, even after filtering through the CPI classifier, there is a close match between the observed peptide 15N atom percent values and the expected amount of isotope incorporation from each media treatment. With the caveat that fewer peptides were identified from the open source search algorithms we tested compared to Sequest, both search platforms showed comparable accuracy in estimated enrichment values for samples with 20 atom percent or less label incorporation. Above 20 atom percent, either poor accuracy or severe loss of peptide identifications reduces the effectiveness of these open source alternatives. To summarize, our findings suggest that fewer 15N variable modifications could be used to reduce compute time without substantial impact on the results, but identification of 15N labeled peptides above 10 atom percent requires consideration of at least some variable modifications. If known, the expected degree of enrichment can guide selection of the variable modifications considered. This work we did here to adapt our pipeline to freely available software broadens accessibility of this bioinformatics solution for tracking assimilation of labeled substrates within metaproteomes.